Afternoon and evening, everyone. I'm Prof Ong. I'm from University of California, San Diego, and my lab is called the Materials Virtual Lab. We are a pure computational lab specializing in the application of materials informatics for materials design. So I would really like to thank Joule and Energy and AI for organizing this symposium. And it is really exciting to see energy and the application of AI in energy taking such a prominent role. And I'm really looking forward to all the great publications that I'm sure will come out in these journals. So for the purposes of my talk today, I'm going to talk about just one of our works, a very recent work, which is called Multi-fidelity Graph Networks for Materials Property Prediction. This work was done primarily by my assistant project scientist, Chi Chen, all right? And it addresses one of the long-standing problems in materials property predictions. So let me start by introducing what is the holy grail in material science, right? So the holy grail in material science is basically being able to predict the properties of materials, starting from is the basic arrangement of atoms in the either molecule or crystal structure. So traditionally, the way that this has been done is that you take you take the structure of either the molecule or the crystal, you put it into computers, and usually you calculate it using some first principles method like DFT, or there are also non-first principles methods like force fields. And what you get out of this computation are material properties. Okay, so things like energies, forces, band gaps, or even higher level properties like the mechanical properties or catalytic activities, and so on and so forth, right? And then you then apply all these predictions to solving real world problems, all right? And of course, this being a Joule and Energy AI symposium, we are one of the major applications of materials are in energy applications, right? So things like lithium-ion batteries, solar cells, superconductors, or there's this recent work that we published in Joule on phosphor materials for solid-state lighting. Now, the next step, of course, is to go beyond just using all these very expensive and large computers and doing these very, very expensive calculations, which, while they are very accurate, they actually are a bottleneck in the number of calculations that we can do, right? So really, where AI and machine learning comes in is to take the results of some of these first principle calculations, and we build machine learning models that hopefully are efficient enough that we can run on even a tiny little laptop. And we can do this for, instead of just thousands or even tens of thousands of materials, we can easily do this for millions of materials. Okay, so we can explore compositional spaces in a way that we have not been able to do in the past. So why is machine learning necessary in material science, right? So let me give you a data history of the materials project. The materials project is this very large database of materials properties that I helped set up in back in 2012, right? So if you look at the history of the materials project, you will notice that that while we have consistently tried to grow the number of materials that are being reported in the database, so for example, if you take a look at the energies, right? So today we have around 130,000 structures and energies in the materials project, okay? And most of these are crystals. However, when we look at other properties that we have begun to compute, the number of properties are actually significantly fewer. So even for something like accurate band structures, we have about half the number of structures with band structures compared to energies. And if we look at other properties like elastic tensors and mechanical properties, those are even fewer. And this is a reflection of the fact that things like elastic tensors are actually much more difficult and expensive to compute than things like relaxations and energies, right? Now, the reason why we need machine learning in material science is that unlike computations, materials design is combinatorial, right? So when we think about designing a new material, we like to try to try all the different types of species that can potentially sit in a site, and that process actually generates a very large space of compositions and structures that we have to explore, right? So if I take a naive way of estimating the number of potential structures for, let's say, a 2 by 2 by 2 cell arrangement of a perovskite cell, and I just consider 10 A atoms and 10 B atoms, I'm already ending up with 10 to the power 7 potential crystals. And this is not, of course, this is a naive estimate. I didn't consider symmetry and all those things, but this just gives you a sense of the scale of the problem, right? So the good news, though, is that because we have built such large computational databases, today we actually have enough data on quite a number of properties to basically try to machine learn from the existing data that we have and basically try to predict everything else. So we can build accurate machine learning models, and hopefully what we can then do is to extrapolate that, interpolate or extrapolate the predictions from those machine learning models to predict for compositions and structures that we are thinking of but have not actually tried to calculate. So the type of machine learning model that I'm going to this is what is known as combinatorial generalization, and this is essentially one of the key strengths of machine learning, right? So what is known as making infinite use of finite means, right? So for example, if we take the 26 letters of the alphabet, we can either write a nice sonnet. So William Shakespeare can, of course, write a nice sonnet, or we can also arrange the same letters of 26 letters of the alphabet and write a scientific paper, right? However, that kind of learning also takes place in the context of a hierarchy of structured knowledge, right? So as scientists, there are many things that we have already learned from our experiments, okay? So there are simple things like the laws of thermodynamics. We know what are extensive properties, what are intensive properties. We have some sense that many properties are local, right? So when we talk about interactions between atoms in general, atoms that are much closer together tend to interact much more strongly than atoms that are much further away. We also have principles of symmetry, right? So things like translation, rotation, reflection, and permutation of identical atoms. We know that when we perform these symmetry operations, the property of the material must remain unchanged, okay? So so this leads us to what is the natural representation of materials? And one of the most exciting developments in recent years is basically using graphs as a natural representation for materials, right? So you can represent the atoms as nodes in the graph and the bonds between the atoms as edges in the graph, right? So when you do that, you can create this graphical representation of you can represent materials as a mathematical graph. Okay, you can have vectors representing the atomic properties and as well as the bond properties, right? Now, in a graph network deep learning approach, basically what you do is that you can create a sequence of operations in which you update the bond, atom, and state properties. Okay. So, and you update them by taking information from, for example, the atoms and bonds to update the bonds. You can similarly do an update of the atomic information, and then you do a update of the global state information, right? And because we do not really know what the functional form of this update function should take, we can approximate them using deep neural networks, and we can then use a standard machine learning algorithms like the backward propagation to train to basically train these functions, right? Now, the nice thing about this materials graph network, or what we call the MEGNet approach, is that it is very modular, right? So each of those sequence of 3 operations is what we call a MEGNet block, okay? And you can stack multiple blocks to generate models of arbitrary complexity and locality of interactions. Okay, and once you actually, after you actually have multiple blocks, what you then have is a deep neural network output layer, output section where you then make a final property prediction, right? So this implementation is actually completely open source, and if you are interested in using it, you can go to our GitHub page at this address to basically check it out, right? So how do the graph networks perform? What we showed in our paper, which is published in Chemistry of Materials back in 2019, is that we can achieve state-of-the-art performance on a broad variety of properties. So here I'm actually showing you just the prediction on materials project crystals. All right, you see that for example, predicting things like the formation energy, we achieve 28 MeV per atom mean absolute error in our predictions, while for something like band gap, we achieve a 0.33 EV accuracy, right? Now, one of the things that is interesting to us is also that in many cases, some of these data sizes are actually much smaller than others. Okay, so for example, remember when I talk about the history of the materials project, we have lots of energy data, but however, for other things like, for example, band gaps, we actually only have slightly over half the data, and for things like the elastic constants like the bulk modulus or shear modulus, we have almost an order of magnitude fewer data than our energies, right? So what we try to explore is basically transfer learning as an approach to improve the convergence and accuracy of our predictions, right? So in our model, we actually use our atomic number as the input for our atoms, but this atomic number is actually then put into this elemental embedding vector, okay? And when we train our formation energy, what we learn is this embedding vector that is a representation of all the different elements in the periodic table. What we found was that this embedding is actually transferable from our formation energy model to other models of lower data, okay, smaller data sets. Okay, so for example, if we transfer this elemental embedding to our band gap model, and then we retrain the model in terms of the MEGNet blocks, we can actually significantly decrease the MAE from 0.38 EV to 0.32 EV in our band gap, and we actually also significantly improve the convergence speed by a factor of 2. Okay, so I'm going to skip past this slide, okay, and I want to talk about a more recent development of our multi-fidelity graph, which is what we call the multi-fidelity graph networks. Okay, so this is let me talk about the data problem in material science, which is that high-value data, either experiments or accurate calculations, tends to be very scarce. Okay, so this is the band gap of crystals. What you see is that, for example, for PBE data, we actually have a fairly large quantity of data. However, when we talk about more accurate calculations like HSE, GLB, or SCAN, the data size is actually significantly smaller. And when we talk about the most valuable data, which is the experimental data, that tends to be one of the smallest data, right? And basically what we want to try to do is to basically try to build a model that allows us to model this high value data as accurately as possible, right? And in multi-fidelity graph networks, what we do is that we take the data fidelity, which is, for example, whether it is a PBE data or HSE data or experimental data, and we embed that fidelity information in our global state vector in our graph networks, all right? And then we do our training, okay? And we can then train the entire model with all the different fidelity data all at once. And what we found was that when we actually build such large multi-fidelity models, we can significantly improve the prediction of our high-value GLBSC, HSE, and experimental data. Okay, if you look at the 1 fidelity compared to the 2 fidelity compared to the 4 fidelity models, you can see that our MAE significantly decreases when we actually use the multi-fidelity approach, okay? And the reason why this works is that when we actually incorporate the large PBE dataset, we significantly improve the latent structural features and the separation and the relationship, the separation of our predicted properties in terms of the latent space of the structural features, okay? Now, we also can use this graph network approach to model disordered materials, okay? So what we found was that when we take the elemental embeddings and we use them as our input for the atomic information, we can represent disordered sites as essentially just a linear combination of the elemental embedding vectors of our constituent atoms, right? And with this, we can then predict the properties of disordered materials, all right? So we actually show that we can predict the band gaps of this these four different systems that there are these four different mixed elemental systems, and we can actually reproduce the experimental trends really well using our multi-fidelity graph networks, okay? And as many of you may know, disordered materials actually make up the majority of the materials that are known, okay? Out of the 200,000 or so materials in the ICSD, about more than 100,000 are actually disordered crystals, all right? So to conclude, today I want to say that I've shown you that in our machine learning for material science, there is a hierarchy of knowledge, okay? There are known inviolable physics and chemistries that we know, okay? And for this, we should encode them into representations where possible, okay? There are some things that we have an intuitive sense of, for example, things like the range of interactions. And for those, we need flexible representations. And for unknown relationships, we can then use machine learning to try to learn them, right? And similarly, we actually have a hierarchy of data, all right? So, for example, we have very, very cheap, less accurate calculations like PBE. And using those, we can actually learn more effective latent representations for our data. We can then use more expensive computations to enhance our accuracy. And finally, we can then try to predict the most valuable and expensive to obtain experimental data. All right. So this is my final slide, and I just want to acknowledge the contributions from my assistant project scientist, Dr. Chi Chen, as well as my group. The work that you have seen are published in these two papers over here. And these are by the funders for this work, as well as computing resources are provided from Exceed. And if you're interested in hearing some of the other talks that we have, we actually have a YouTube channel for our lab over here. Thank you.